Okay, so you're returning to this video having done some work on limits and seeing how we can see how a function approaches a certain value when we allow x to approach a certain value, even if it doesn't exist at that point. Wow, it's confusing stuff, isn't it? But you'll see how it works out in practice, and I'm going to start the ball rolling with this in this video. You can see I've got my 2 points really close together here. And you can see that I can create a line segment from there. And again, don't worry about the complexity of this. It's just a matter of seeing that this does exist. So I'll move H out a bit further so we can see that this line is between the two. I'm also going to do this as well, turn this one on. And it's changing it from a chord to a secant line, but it's the same sort of thing. If I move this up and down, there's that secant line or the secant, and as I move it closer and closer and closer together, we can see that the secant is getting really close to just touching at one point. Now I need to introduce a new word now as well. So if a secant line cuts through 2 points in a function, what do we call it when the line just touches at 1 point? Well, we call that a tangent line. So whenever you see the word tangent line or tangent, calculate the tangent at x equals 3 or something like that, it's saying come up with the straight line which touches the graph at a particular point and no other point, like so. So can't go through like that, can't go through like that. It's going to touch on the graph and keep on going at that particular point. I'm going to zoom up so we can sort of see this is still a secant line. And as we've discussed before, I can't make this a single point because then it disappears, right? But clearly, a line must exist that has those properties. And I'm not going to explain why, but I'm going to pop that on. There it is there. So here is an example of a tangent line. The points are at the same coordinates. There is definitely a straight line that goes through, that touches at that point and then keeps going. And based upon what we've done earlier, I hope you can see that it's not a hard thing to say that if we can work out this tangent line, then the gradient of this tangent line, which is the same all the way along this blue line, the gradient of this tangent line will be exactly equal to the gradient at that point. And therefore, what we have is a definition, if you like, for working out the instantaneous rate of change at a point. It is whatever the gradient is of the tangent at that point. And what we need to do is work out how on earth do we work out this tangent line. And some of the work we've been doing leading up to this point will now be pieced together so that we can see it. So let's start by looking at this secant line again. I'm going to go to Air Sketch and we're going to start talking about this thing called a gradient function, because we can see, sorry, I'll just go to the right place. We can see that the gradient itself will change depending on where x is. So at the moment it looks like this, but if I move x around, we can see that secant line is getting steeper or flatter as we move x around. Okay, so it's only the same when I've got the same gradient as this one here. So I'll turn it off so it's not confusing. Okay, so as I move x around, the gradient changes, and therefore we can talk about a gradient function, a function which, if I put in a value for x, it will return, out will come the gradient at that point. So there's a little bit of language here. It's a gradient function, and we're going to use the notation f dash of x or f prime of x, you might see it. There's other notation as well, which we'll get into at another time. So f dash of x, but let's just consider it as the gradient over those points. So one of the points was, we know that the gradient in general is determined by subtracting the change in y values and we're going to divide it by the change in x. Well, the smaller point, the point that's lower down, let's call that f of x. And so we're going to subtract x away on the bottom as well. The other point, so we've got x and f of x here that we're subtracting away. What are we subtracting it away from? Well, a little bit further along, we've got x plus h, and f of x plus h, remember, is like the y2 value. So if I go back here, I can put in f of x plus h here, and I can put x plus h here on the side. But those brackets down the bottom don't really help us. There's nothing to evaluate there. X plus h is just x plus h. So I've got f of x plus h minus f of x on top. So that's the change in y. And on the bottom, I've got x plus h minus x. Like so. So you can see, I hope, that effectively the x and the minus x cancel out. And so we end up with this function here. So we've got f dash of x is equal to f of x plus h. That's the y coordinate a little bit further on from x. And f of x, that's the y coordinate at x. And it's just all over h because the x's will cancel out. Great, excellent. And we know to work out that tangent line, we need to get x plus h and x as close as we can. But again, even if we made h 0.000000001, then although we would have a really close approximation of the gradient at that point, we would not have the gradient at that point. To do that, we would need h to be equal to 0. And if we let h equal to 0, we run into this discontinuity again. The bottom of this fraction would be equal to 0, and so it wouldn't work. So what we end up doing instead is we use our limit notation, and we say what is happening to the function, the gradient function, I suppose, what's happening to the gradient as h approaches 0. So we need to have this limit notation. And I should have put it in here all the way along. I might just do ... here to show that it was missing. It's really important you get this notation right. If you're asked to work out the gradient or the gradient function using what's called first principles, that's what you're asked to do. You're asked to write f dash of x equals the limit as h approaches 0 of this. And we're going to use a very similar technique as you were doing in exercise 17F, was it? Where you are going to manipulate the fraction until the denominator has disappeared, and then you're able to work out the gradient. It's quite clever. But before we do that, let's have a look at it in action here on this graph here. And now I'm going to start unpacking what these functions look like so you can make more sense of them. They look horribly complicated, but honestly, they're not. This function here, which I'm going to turn off in a second, is really just the point gradient form. You can see I've got y minus y1, which is f of x0, and I've got x minus x1, which is x minus x0. And then here, what I've got is y2, x0 plus h, minus y1, f of x0, all over x0 plus h minus x0. x0's cancel out, just like I showed you a second ago, leaving you with h. So effectively, in other words, this bit here that I'm highlighting, that is the gradient of the straight line, of the secant. And again, as I mentioned to you, as we let h get equal to closer and closer to 0, yes, it does start to approach the gradient at the point x equals 2, but it isn't quite able to get there because once h equals 0, we're dividing by 0, and therefore this stuff's up. Okay, so have a look at what I've got here. Looks a little bit simpler, but now I've got this notation that I've talked to you before, and that is y minus y1, f of x0. I've got x minus x1, x minus x0, and I've got f dash or f prime. This is that gradient function, which I haven't shown you how to work out yet, but I've said now evaluate the gradient function at x equal to 0. And now we've got a tangent line. So this orange line is a secant line as opposed to, this orange line is a tangent line instead of a secant line. So even if I let h equal 0.0001, I'll even turn it on so we can see the secant. If I zoom in really close, we can see, the computer might actually not allow us to see this, but effectively there is a blue line here which is just on the either side of this. Here we go. So there's the red line, there's the blue line, which is passing through x equals 2. Oops, I'm zooming out the wrong way, sorry. So it's passing through that point, but then it's also passing through here as well. Whereas the orange line, can you see that even just from this point here? The orange line is not passing through that point. And as I scroll, I'll turn off the secant line so it's really clear. As I scroll, you can see that there's a definite gap between the red line and the orange line. And I'll just zoom out and zoom in again. So that orange line continues, and as I zoom in here, you can see that this is the point x0, x equals 2. We can see that the orange line is, I can zoom in as much as I can actually. The orange line is just touching the red line and then continuing on. And the only reason why I can't show you any more than that is because it's run out of zoom, sadly. So there you go. So this orange line is a gradient line, a tangent line. The gradient of the tangent is the gradient at that point for reasons we've gone into before. And if I move x0, which at the moment is 1.3, I should have been 2, sorry. If I move it, you can see the orange line goes around the function like so, including here at the turning point, we've got a gradient of 0. So the orange line is just the same as the x-axis in this instance. So it's following that point around, touching the graph at that point, but not touching the graph anywhere else. Okay, so we can see that as the f dash of x0 there. So evaluate the gradient function at x0, and that gives me the gradient at x0, and the gradient of the tangent line at x equals 0. Sorry, x equals, in this case, 2, or whatever it happens to be. Okay, so that's the name of the game. Now, I've got some good news and bad news from here. The bad news is that calculating this gradient function by using limit notation, you know what? It's not too hard as long as you don't get confused with what this means, f of x plus h. Remember, this just means we're substituting a value x plus h instead of x into the function, so it's like a transformation. It's not too hard, but it's quite tedious, and you do need to know how to do it, but only for fairly simple functions. The good news is that there is a rule which allows you to work out that gradient function really, really easily. So I'll briefly introduce you to this rule. In fact, there are a whole bunch of rules for working out the gradient function, and this set of rules and techniques is called differentiation, and this branch of mathematics is called differential calculus. And I'll show you the most simple rule, and that is if you've got f of x, so this is called the power rule for differentiation. If you've got f of x equals x to the power of n, so x raised to a power, then the gradient function is equal to n multiplied by x to the power of n minus 1. Really simple. So, for example, if f of x equals x squared, that's the graph that we just have been looking at, then f dash of x, or f prime of x, the gradient function, is equal to 2x. So if I said, what's the gradient at x equals 2 of f of x equals x squared, the answer would be f dash of x equals 2x, f dash of 2 is equal to 2 multiplied by 2, which equals 4. So the gradient would be 4. So it's a really straightforward rule. And on Friday, what I'm going to do, or next lesson, if this is not Friday, next lesson, I'm going to show you how we can use this first principles approach in order to get a glimpse as to why the power rule works. So that's a bit of theory that's really important for you to get a handle on. And then I'm going to get you to practice using the power rule for a bunch of different problems. And you can see the actual calculation of the gradient function is not too hard. It really isn't. But understanding what it means in terms of these functions here and what all this means, that's where it gets a bit tricky. P.S. If I just do this, it should work. Y minus f of x0 equals 2x outside of, 2 times x0 outside of x minus x0. There's the green line, and of course, as I move x along, the green line also follows, as well as the orange line. Okay, that just goes to show you that the derivative of x squared is 2x. It does effectively become the gradient of x squared. Okay, so we'll explore this in further depth next lesson, but for this lesson, I think that's enough theory for today.